Okay, still trying to keep an open mind on the whole flat earth, round earth question. I'm going to try to explain briefly what I would expect to see, what I would expect to happen at sunset on the equinox on a flat earth. Today being the equinox seemed like a good day for it. By the way, as CNN was handy enough to point out this morning, there are some slight variations in the length of the day even on the equinox, but they're minute. Literally, they're minutes. Out of a 12 hours of sunlight, if you go to the right place on the earth, you can squeeze out maybe 18 more minutes of sunlight. 18 minutes compared to, let's see, 12 hours is 720 minutes. That's not much. So briefly, what I would expect to see in the equinox at sunset. So we have labeled here the North Pole. We have a circle. Okay, so it's not a very well drawn circle, but a circle representing the equator of the Earth. And at noon, the sun would be over some particular part of the equator. It would be straight up. Someone could stand on the equator. They would see the sun directly over their head. Let's imagine that that person is on the same line of longitude that I am. Somewhere there's got to be a point on the equator that's on the same line of longitude that I'm at. But I'm a little bit north of the equator. I'm about 42 degrees north of that. Now for someone on the equator, they would have seen the sun rise when it was here over the equator. This represents the actual equator. This represents the North Pole, or the center of the Earth if you prefer that terminology. This person on the equator would have seen the sun rise when it was here. They would see the sun directly overhead when the sun is directly overhead here, and they would see it set when it gets here. That's the actual path that the sun would appear to take over the Earth. People standing along this curve would see the sun directly overhead at various points throughout the day. At essentially 6 a.m., well, 7 a.m. because I'm on daylight savings time, people standing here on the equator would have seen the sun directly over their head. At 1 p.m. for me, people standing here would have seen the sun directly overhead. At 7 p.m., people standing here would see the sun directly overhead. So I was observing the sun this morning as it rose, and it was over here, over the equator. 6 hours later, it was here, definitely to the south of me, but as high in the sky as it's ever going to get today, and now it's declining in a little curve towards the west and setting. When it sets, if we first look at what someone at the equator should see, what I would expect them to see on a flat Earth, the pole here is the same distance from the equator here as it is from the equator here. So this allows us to make a nice isosceles triangle. This side and this side are the same length. You can do a little trigonometry, or you can just try drawing isosceles triangles. If those two sides are the same length, and this should be a right angle because we've gone a quarter of the way around the circle in 6 hours. In 12 hours the sun would be here, another 6 hours it would be there again, and 24 hours later it'd be essentially back directly over the head of the person here. 6 hours, 12 hours, 18 hours, and 24 hours. That's how I am coming to the conclusion this is a right angle. It's a quarter of a circle because we've gone a quarter of the way around in 6 hours. So at sunset, a person at the equator should be able to measure a distance between where they would see the North Star, Polaris, and the point where they would see the setting sun, of 45 degrees. They could simply get out and mark where their feet are, a point somewhere on the ground that is basically by sticking a stick in the ground, they can look and see that's the direction where I saw the sunset. Okay, feet here, sunset was off in that direction, as marked by the stick, or maybe by a chalk line on the ground. They can then wait for Polaris to come out when it gets a little bit darker, and they can look up in the sky and see Polaris, which for them is actually going to be pretty close to the horizon, and mark that on the ground as well. Draw a line from where they saw the sunset to where their feet were in both cases, and then to where they see Polaris over the horizon, and measure the angle. What I would expect them to see on a flat Earth is about 45 degrees. Now, I'm not at the equator, so I'm not going to see 45 degrees, but neither am I going to see 90 degrees because I'm also not at the North Pole. On a flat Earth, I would expect that what I'm going to see, I don't have reliable distances done by people using a flat Earth model. This is just sort of zooming in on the above, but I would expect to see the sunset. Me here, I can observe the sunset and mark a spot on the ground towards the horizon. Draw a little chalk line in. I can then wait for Polaris to come out, hopefully with the help of a friend, and have them stand on the ground so that I can look up at Polaris, bring my head straight down just by nodding my head up and down, go from Polaris down to the ground, get my friend to stand there, and mark the direction that Polaris is relative to me. Now, true west for me, by the usual definition, would be off in this direction, the direction that I would get if I were facing Polaris and then turn 90 degrees to my left. That's true west. What I'm saying is that it seems to me that today, on the equinox, as on most days, when the sun sets by passing around the horizon or passing around over the top of the equator, I should see the sunset at some angle, certainly away from true west, because the only place that's going to, you can see as you got closer and closer, if we had a series of people along this line of longitude, this person at the equator would see a 45-degree angle away from true west. These two angles being the same, in order to make up a 90-degree angle there. As we got further towards the pole, this angle away from true west should get smaller and smaller, but it's not going to actually go to zero until you get at least very close to the North Pole. So, what I hope to do this evening is go out and actually measure this. Watch the sunset, mark a spot on the ground, watch Polaris come out, mark another spot on the ground, and measure this angle here, which I'm going to label beta, and consequently measure this angle here between true west, taking my direction towards true north and turning 90 degrees to the west. That's the path that I would have to follow if I was in an airplane and I wanted to follow and fly around the equator. I'd have to start off from the equator and go towards true west, which would be a tangent line to this circle. So there's true west, which is 90 degrees away from true north, which is easy to find because of the North Star. One more time. Sorry, I'm trying to talk fast to keep this video short and not succeeding. But there's true north, the north of the pole star. That's easy to find. Normally I would find true west by simply turning 90 degrees to my left, or counterclockwise, and that would be true west. And then there's the west of sunset on the equinox, which it certainly seems to me should not be the same place as true west. It's going to be off by some angle. Not 45 degrees off because I'm not at the equator, but certainly off by some angle, which I hope to measure this evening. That, to me, is the way that this seems like it should happen on a flat Earth. So I'm going to go out this evening with some chalk and mark the position of the sunset and hopefully the position of Polaris if it's not too cloudy. I'll let you know how the experiment turns out. Thanks.